Now, I will show you another important application of the Golin formula. Okay, this is a two-dimensional Brouwer fixed point theorem. Brouwer fixed point theorem is very famous result. A very important achievement in 20th century's mathematics. The theorem says that if f is continuous, here B is the closure of the unit ball. That is the closed ball, unit closed ball. Then it has a fixed point. So this is very simple statement, but very difficult to prove. Here our B is a n-dimensional ball. Okay, n-dimensional. So this is the n-dimensional case. That is the most general case. Using Golin formula, we can give a proof, a very easy proof of the two-dimensional case. So to prove the Brouwer fixed point theorem, it suffices to prove the proposition. There is no continuous map say C from B to its boundary such that phi x equal x for x on the boundary of B. If you can prove this proposition, you can prove the Brouwer fixed point theorem. Okay, why? It is very simple. So from proposition, we prove the theorem. Okay. Here, if it is not true, if theorem is not true, so if f has no fixed point, then for any x in B, the x will not equal fx. Maybe okay. So therefore, look at this picture. This is B. For any x in B, fx will not equal x. Therefore, fx is another point. So since fx is not the same point of which x, we can determine a segment from fx to x. Start from fx, go to the direction of x and extend. You will have a segment, extended segment. A race, it will intersect with the boundary of B. At some point, this point we say phi x. For different x, you will have different intersection phi x. That is, we can define the map. Let phi x belongs to the boundary be the intersection of the segment starting with fx and in the direction of x. I use this notation to indicate the ray starting at fx and go toward x and extended infinitely. Okay, this ray is denoted in this manner. So this ray will intersect the boundary of B at a unique point. This point we call phi x. So we obtain a map. Phi. Every point in B, the image of x is lie on the boundary of B. Therefore, this is a map from B to the boundary of B. And this map, if x is a point in B, if x is a point in B, what's phi x? So if x is already a point in B, then fx is here. So the intersection is precisely x itself. This means phi x is precisely x. Okay, so our argument tells us that if the conclusion of the Brouwer fixed-point theorem is not true, then we can construct a map from B to the boundary. This map has the property when x belongs to B. When x belongs to the boundary of B, when x is a boundary point, then phi x is x. So this is a contradiction with our proposition. Our proposition says that there is no continuous map from the closed ball to its boundary, such that this map makes every point unchanged on the boundary. Okay, so this contradiction tells us that the Brouwer fixed-point theorem is true. Therefore, to prove the Brouwer fixed-point theorem, we only need to prove this proposition. And of course, there is an issue we have not mentioned. That is the continuity of this map phi. But because f is continuous, using analytic geometry, you can write the expression of phi x, and then you will see that this phi is continuous. Okay, so the continuity is true for the map we construct here, phi. And this proposition is about a continuous map, but continuous function can be approximated uniformly using smooth function. Similarly, continuous maps can also be approximated by smooth map. Therefore, if you can prove a smooth version of this proposition, it will not be very difficult to get this continuous version. So we satisfy ourselves by consider the smooth case. So we will use the Brouwer fixed-point theorem to prove the following proposition, which is the smooth version of the proposition we used to prove the Brouwer fixed-point theorem. And of course, we consider smooth version. And because we want to apply the Green formula, we can only study two-dimensional case. Okay, so this is our proposition. Let B be the unit closed disk. That is a two-dimensional ball. Then there is no twice continuous map such that the image is contained in the boundary, and the restriction to the boundary is the identity map on the boundary. So this is the two-dimensional smooth version of the proposition we just used. The last statement, the last condition means that x belongs to the boundary, then fx is x. Okay, so this is the two-dimensional smooth version. It seems difficult to prove this proposition, but actually it is not so difficult. Let's see the proof. F is a vector valued function, two-dimensional and two variable, because the variable is from B. That is a point, two-dimensional point, and the image of fx is in R2, also have two dimensions. So f can be written by component f1, f2. Then for xy in this closed ball, we have this is 1, because the image is lying in the boundary, because fx, oh no, sorry, accident. Now we are normal. Because for xy in B, our fxy belongs to the boundary, that is the unique circle. So the sum of the square root of the coordinate f1 and f2 is 1. Okay. Now we're taking derivative with respect to x and y. We obtained the derivative with respect to x is f1 maybe I will f1x plus f2x equals 0. The left hand side, the derivative of f1 square with respect to x is 2f1. f1 with respect to x. The 2 we can cancel because every term will give us a 2. Okay. So similarly, the derivative of this with respect to x, 2f2 multiplying the partial derivative of f2 with respect to x. The 2 will also cancel. So we have this inequality. Similarly, taking derivative with respect to y, you will obtain the f1y plus f2y is also 0. So we have this result. This result, because f1 and f2 is not 0, because it is a point on the unit circle, it is not the origin. So f1 and f2 cannot be 0 simultaneously. They can at most one of them be 0. Either two of them are not 0, or at most one of them 0. You could not have both two of them are 0. This means that we consider this as a system of linear equation which are unknown. f1, f2 are unknown. The coefficients are the derivative. So this is a system of homogeneous linear equation, has no 0 solution, because f1, f2 consisting of vector which is the non-zero solution of this system of linear equation. So we must have the by the Coulomb law, the determinant of the coefficient matrix must be 0. Since f1, f2 is not 0, the determinant of the coefficient matrix, that is f1x, f2x, f1y, f2y, is not 0. But this determinant, what's this? This determinant is f1x, f2y subtract f1y, f2x. This can be written by f1, f1, f2y subtract f1, f2x. Okay, you expand the right hand side. You will have the f2yx and the f2xy. f2yx come from differentiating this with respect to x. These two terms are equal. So these two terms, when you expand the partial derivative, when you expand the expression, the final expression, those terms involving second order derivative cancel. Only the first order term survives. That is the left hand side. Okay, so this determinant is not zero. So it's zero, sorry, because the system has no zero solution. So this determinant must be zero. So this is zero. Tell us that the integral of the final expression over the is zero. f1, f2y x subtract f1, f2xy. This must be zero because the integral is zero. But applying the Green formula to this double integral, this will be the integral over the boundary. In the Green formula, this is our Q, this is our P. So applying the Green formula, we have P dx plus Q dy. That is f1, f2x dx plus f1, f2y dy. Okay, so we conclude that this line integral over the unit circle should be zero. Okay, but on the other hand, we can compute this line integral explicitly and find that it is pi. It is the area of the unit disk. So this is a contradiction. Okay, this contradiction says that the statement of the proposition is valid, therefore complete the proof. So I will compute this line integral in the next video.